recording. Okay, welcome back to another EMP session. Today we're going to be picking up with kind of the same topics from last time, trees and recursion. So we looked at recursion last week, and then during today's session we'll look at how you can use recursion specifically with trees. Okay, so the slides are not up yet on the course website, and I just realized that. I will post it as we're going through the first problem. Most of the starter code won't be necessary to run it anyway, so I'll post those as we're kind of getting started. Okay. And as always, you can use the homepage for the website to do practice. So first, I guess, a review on trees. What do we use them for? Remember that trees are kind of that special kind of data structure. At this point, you've learned about a lot of data structures, right? You've learned about hash maps, you've learned about linked lists and array lists, and even arrays. So you have all of these great toolkits with you, but trees are special in the sense because they have kind of a hierarchy to them that we can use to represent objects. And so trees kind of look like this. Essentially, this is kind of a more structured one, but the idea is the same. So each tree has a couple of nodes in it, or it might have not have any nodes, but it has a couple of nodes, and each node represents some sort of data type, data point, and then there's some connections between each of these different nodes, and there can be all sorts of different connections, right? You can have parent nodes, child nodes, leaf nodes, root nodes. So we'll get to some of those terms in just a second. The other thing, I guess, to look at is they're really useful for a lot of different real life situations, which he talks about in the lecture a lot. But like, for example, you could represent a company hierarchy. The HTML DOM is also kind of represented as a tree. And then you can think of even like family trees. There's also different use cases in the real world where you might want to represent something in the form of a tree. Okay, so quick review on that, trees. All right, so now then maybe let's take a look at some of the popular tree terms, right? You have the root, which is the first node in the tree, usually at the very top. So in this tree, the root node, I think, would be the CEO. And then we have the parent node, which is like any node that has an edge that points to another node. So, for example, CTO is the parent node of software engineer. CEO is the parent node of CTO. And then I guess I want to point out that in this particular diagram, there aren't any arrows. They're kind of like just edges pointing to different places. You're going to see variations of the trees without arrows and with arrows, just depending on what you're modeling. But it should be fairly intuitive to you in this tree structure what the parent is and the child is. Usually we will draw it from the top bottom, at least in this class. And the arrows basically indicate where the child is and where the parent is, if there are arrows. Otherwise, you can kind of look at the general structure and tell. And then, so yeah, if you know what the parent node is, you know what the child node is, right? The child node is just any node that has a parent node. And then you have like the leaf nodes, which are any nodes at these bottom where you don't have any descendants from it, and it's kind of the end of the tree. And then, and last but not least, but it's a very important concept to know, the height or the depth of the tree as we define in this class, is the distance from the root node to the farthest leaf node. So you'll see it used both ways. They mean the same thing. The height and the depth of the tree are the same. Okay, so that is my very quick review on trees. Any questions so far? Cool. Sounds like there isn't, which is awesome also. Okay, so now I guess we'll get a little bit more specific and look at a special type of tree, the binary tree. So again, they're kind of the only kind of data structure with trees, at least, that you guys will be working on in this class. There are a lot of other kinds of trees, though, like red, black trees, and a lot of different kinds that I'd like you don't even use like all the time, but they're really useful for specific situations. And this particular tree, the binary tree is unique because it is subject to the restraint that any node will only have up to 2 children. But you can have less than 2 children, of course. So this is what the general structure for a binary tree looks like. Every node has a value. That node will have a left and a right pointer sometimes, and the left pointer points to the left subtree or the left child, and the right node points to the right subtree or the right child. So, yeah, binary trees. This is going to be the only kind of tree you encounter here. Again, sorry, I'm repeating myself now. Yes. So let's talk about how we can use recursion and trees, right? So we've learned about in class, I think up till this point, right? I think we learned about on your class on Friday and Thursday, possibly. Yeah. So on your class on Friday, you guys took a look at how to use trees with recursion, and they're just a really great way of defining things out because trees themselves are defined recursively. So you can think of it as like every node is kind of, I guess when you say defined recursively, it's hard to understand, but you can think of it as every node points to like another left or right child, right? And so you can call the left or right child on your child node also, and eventually you end up with kind of a loop where you're going to every node if you call a method on the left and right child enough times. And then you can also stop by determining if you don't have any new nodes to go to, or if you are like the root node or something like that. So their trees are defined recursively, and so they make for a good data structure to use alongside with recursion. And then, so since we're here on this slide, I guess we'll also recap some of the major steps that we have to do with recursion, right? Recursion is all about breaking the problem up into like smaller pieces, and then using those smaller pieces to solve the ultimate problem. And you can do this with essentially a base case, and the base case is kind of the first thing that you typically test for in the method, and that is the smallest problem that you can solve. So sometimes it'll be something like a check for null, for example, or in the Fibonacci sequence problem that we did, we checked for if it was 0 or 1, and then based off of that, we returned something different. And so there's a base case, and then there's some other cases that are a little bit bigger than the base case that you can solve by calling the same function again recursively. But identifying the base case is kind of the key thing that you need to do to figure out how you need to do the recursion. So yeah, recursion is all about making things smaller, and trees are handled well with recursion. So enough of me lecturing on about this. I'm sure it's not that interesting. Let's do some practice problems. All right, so we're gonna ease into it. The first one is kind of straightforward. Here is a implementation for kind of a node inside of a tree. You have the left, right pointers, and you have like some sort of value in each node, right? And we're giving you the structure to help you figure out how you would want to write a tree that, how you'd want to write a method called find height that takes in a root of a tree. The root of the tree is a node, of course, and so you have this root that maybe has some left and right children. You have to figure out how are you going to recursively find the height of the tree here. So yeah, this one will be a little bit simpler than the other ones. So that is going to be the first question. Let's do 10 minutes on that one and regroup. And in the meantime, I'll post the slides up on the website. And then just let me know if you finish the problem earlier than expected. Okay, the slide should be up now. Okay, so I think we're a little past time. So let's go ahead and review the solution. Those are the solutions. Let me hide those. And I'm going to copy and paste this over. Okay. All right, so how do we figure out the height of a tree with recursion if we're only given the root? Okay. So my approach to this would be to figure out when you would stop, right? When you would stop recursing. So like figure out the base case. And figure out how to make problems smaller, basically. Right. So typically when you think about trees and recursion, how would you make the problem solver smaller? You would look at a subtree from that original tree. And when I say subtree, I mean kind of a shorter version of this tree without one node or without a few nodes. And so that would be your left and right trees. So you're going to want to think about maybe calling find height on the left and right children of the original root node. And so I would say maybe first I'd look at the first node, and then to figure out the height, I might want to go and look at this section of the tree. And then I would also want to look at this section of the tree, right? Like the height of the tree will depend on whichever one of these is longer, basically. In this case, I think they're the same. But if you had like maybe one more over here, then you would want to basically count how far it takes to get to this very last node. And you would bubble that number back up to this original root node, right, when you do the recursion. And you would say, okay, let me call find height on this node right here on 8, essentially, the left child. And then the left child would be like, oh, I have 2 children. I have a 5 and a 10. And you would call find height again on the 5 and the 10. And so at this point, you have reached kind of the ending point. There's nothing left. So the left and the right subchild of this node, for example, would be null. And that is your base case, right? Like if it's null, you know that you can just return 0, for example. And so you would return 0 here, and you would return 0 here because they don't have any children. And at 8, you would say, at 8, I want to convey when I come back from that recursion on the stack, I want to say to this node that I have had one is the length here and 1 is the length here. So I will say that I want to do +1 on the left subchild and the right subchild. But I don't want to do +1 for both of them. We want to do it for whichever one is longer. So maybe I'll write out the code so far with what we discussed. So if you're at a node, which is just in this case, if you're at a node and that node is null, I would just return 0. Okay, so you're at a node that doesn't exist, basically. If you're not at a node that doesn't exist, you're going to want to do something like int left height, and you want to do int right height. So now you're going to find the height of the left subtree and right subtree. That's how you're making the problem smaller. So you're just going to call find height on the left and the right. find height on the left in the subtree. How would you do that? You'd have the root, which is the current node, and then you'd call left dot left on that, and then you'd have find height, and then you'd have the root and the right on that. So now you've called the left and the right. Now you got to figure out how you're going to actually calculate during each kind of bubbling up what is the current height. So if you were here in 8, what's your current height going to be? So if you're looking at your left subtree's answer and your right subtree's answer, your height that you want to tell 11 when you're bubbling back from 8 to 11 is you want to say whichever one is the bigger height, right? Because bigger or the same height, essentially. So if they have the same height, it doesn't really matter. But if the left one is larger than the right one, then you want to say my current height, because the height is the distance, like the longest distance from the root to the leaf node. My current height is this left height's answer. So I want to figure out which one of my subtrees had the greater height. So if left height is greater than right height, then I'm going to take the left height and I'm going to add 1 to it. And why would I be doing that? Because so I'm at 8 and so I'm at 8. I just did the recursive call for 5 and 10. And 5 told me I had 1. And then 10 told me I had 1. Let's say 10 had 2 left. Let's say there was another node down here. So 5 told me 1, 10 told me 2. Now 8, we're at 8 in the stack trace for this recursive call. We're at 8. And 8 is now going to bubble back up to 10. 10's call on 8 left subtree. And so 8 is not going to want to say that it has 1, its height here is 1. You want to say its height is 2. So it's this one after 10 plus another node down here. But then you also have this edge from 8 to 11. So it's going to want to say my height is my left subtree height plus 1. And if the case is the right subtree is greater, then you want to say right subtree plus 1. So whichever one is greater, plus 1 is what you want to return to the node above the current node. Okay. Oops. That's pretty much it for the height problem. Oops, there's a bunch of okay, great. Any questions on that before we move along? If that was a hard problem for you, let me know. We'll take our time with the second and third one. I do think the second one is a little bit harder than the third one. But if there are no questions, I'll keep going. Feel free to stop me if there are. Okay, so the second question is finding the sum of the left leaves in a tree. right? So you're going to be returning an integer, which is going to be the sum of all of the left leaves. And so when I say the sum, I mean, we go back to our diagram, you would just be adding up all of the values of the left leave for every single node. So even though there is a right, even though there are some right nodes here, you still have to check to see if they have any left nodes. If they do have any left nodes, you have to include them in the sum. So that's what this question is going to be about. It might be useful, so you can use recursion to solve this problem, but you might want to have another function outside of this function that you can use to define your recursive case. So you'll have this function, but have this function call another function that will actually handle your recursion for you, because this this current method might not be enough for you to do your recursion, basically. I'll say that. So yeah, I know this one is a little bit tougher, so take your time. We'll do 10 minutes on this one also. Okay, I'm going to go ahead and start reviewing this one kind of in the interest of time. Okay. So public class, public and sum of left leaves node root, right? So again, we're given kind of an implementation for a node that has a left and a right node, and then also like the current value, right? So that's what's given here, these three things. So I guess the first thing you can kind of maybe write out is if the root, the current node is equal to null, then you're just going to want to return 0, right? And that's just like you don't have any leaves, you just have null, right? And then now we need to figure out essentially how we're going to count the left nodes in the subtree. So first of all, if you're wanting to count the left, sorry, not to count the left, if you're wanting to sum the values of all of the left leaves in the tree, you have to figure out if it's a left node, essentially. That's first and foremost, right? And then if it is, you want to use the value, but you still have to revisit all of the nodes in the tree until you can find out if it is a left node or not. So I guess my approach to this would be, first, I want to look at the left subtree, and I would want to look at the right subtree. So whatever method I create needs to check both of them. And if you get to the very end, so you get to a leaf node, and how do you know you're at a leaf node? Because there is no left and right subtree. So you check if it is a leaf node. If it is a leaf node and it is a left subtree, so here it is a left subtree, you need to return this value 5. If it is not, if it is a leaf node, again here, this is another leaf node, right? But this leaf node is not a it is not a left leaf, right? This is a right child of 8. So in that case, you don't want to use the 10 in your summation. You just want to use 0, like you just return 0. So that's a key step right there. You have to figure out what is a leaf node. You have to figure out if it is a left leaf node. And if it is a left leaf node, you need to use the value. Otherwise, you don't need to use this value. Okay, so that gives you some clues right there off the bat about your base case. Right, your base case is it is a leaf node. So how do you identify if something is a leaf node? If you have a node, let's call it root, and its left child is equal to null, and its right child is equal to null, then you know that you are at a leaf node. Okay, so that's one criteria. We also need to figure out if is it a left, are we at a left subtree basically? Are we on the left side of this, or are we on the right side? And we can't really tell that from the way that it's currently implemented. Like we need some way of keeping track of it if it is left or right. And the easiest way to do that is, and this might not, this is kind of that tricky stuff that if you didn't think about it, or if you weren't really familiar with how to do recursive problems, you might not realize that this is necessary, but you can create like another method called, you know, whatever you want to call it, calculate, or yeah, calculate trees. Let's just call it calculate trees. And you can take in a node root, right? And you can say inside of your node root, whether you can add like a boolean that says, okay, is it left? Okay, and I'm going to just create like this empty shell method. And then let's move our base case inside of this empty shell method. And now I have some sort of variable in my method. I haven't figured out what that method's variable is going to be, like how we're going to implement this is left, like what it even means. But let's just say that it has some way of checking if it is left, if it is a left child. So in that case, I would say if is left, so if it is left, then I would return value of that node, right? I would return root dot value. I know it's called root, but this is just like a node for the tree. Otherwise, I would just want to return 0. And the reason why I do that is because I only care about those left leaves, and I don't care about the right leaves. So I ignore the right ones, and I keep track of the left ones. So it's kind of the base case. And then the recursive case, right? So let's say that you have let's say you're at the top, right? At the very top of the tree. You're going to want to look at this side of the tree and this side of the tree. But you know that when you're checking this side of the tree, you know that it's left because you're calling the root dot left, right? So that's how you can keep track of whether it's left or right. And whatever results that you get ultimately from here, you can just keep adding them up after every like level after you complete. So let's say you find that 5 is one of the left leaves, and you have that 5, and you have that 8, and you add them together, and eventually you come up to 11, and you say, okay, I have 13 as my sum there. Sorry, 8 wouldn't be your sum because that's not a leaf, just 5. So you need some variable to keep track of the total sum. So I would just call it int total or 0. And if you have that, and then you're at the root, then you might want to split it by whether or not it is a left or right subtree. So I would do like a total plus equals cross plus equals calculate trees. And now I'm going to do the root dot left. So here I'm going to look to left. So look at the left subtree. And you also want to look at the right subtree. Okay, and then in this case, I'm calling the recursive function calculate trees, and I'm giving it an is left. Right? So I'm going to say this is true because it is the left subtree. And I'm going to do the same thing with the right subtree. Calculate trees with the root and do the right. And now it's false. Now I'm passing in false because it's not the right subtree because I don't care about it. Okay, so I've done all of this and I've calculated the total that comes out of both of my subtrees. So then I can just return that total value. That's the main process here, right? You're going through each of the subtrees from a node, and eventually you keep doing that until you get to a leaf. And you get to a leaf, you check to see if that leaf is a left leaf. If it is, you take that value and you bubble it back up and you add it to the total from the previous call. And you keep adding those totals up till you get to the top of the tree. And then you return that total. That's kind of what's happening here. So a couple of things that we need to figure out, right? I've created a method called calculate trees, but how do I even call that from sum of left trees, which is an original function? You can just say, so there are many different ways to approach this, but since we gave you this original function method to work with, I would call calculate trees here. And I would give it root, and I would give it false for is left because it is just the root of the tree. It's a parent, so it doesn't have the right. And then I would return the value from that. So now you can do the recursion in a different method. You can leave this method alone. You don't have to change anything about it. And this will handle the recursive parts of it for you. And then I think the only other thing that we need to also do is you also need to check to make sure that there is a left and a right. So before you call the root.left and the root.right, you can just have a check to see if root.left not equal to null. If it's not equal to null is when you should be calling this because otherwise it doesn't make sense to call it. So just do root.right, right here, and then you should false. That is how you calculate the sum of the left in a tree. Okay, I know that was a lot. It's probably very confusing. It took me a second to also figure out how to go about this. So if you're struggling, don't worry. This is a hard topic. Recursion is always difficult for people when they start. But once you get more practice with it, you're going to start seeing the pattern that you're looking for, right? Between this question and the previous question, you might have noticed that we're doing the pattern of calling the left and the right subtrees again and again. And we're doing some sort of calculation after that call is returned, right? In this case, you're taking the total and you're adding it together. In this case, you're adding 1 to it. And then the base case is always just some way for us to know when we need to stop running our loop, our recursive calls. So once you start to get a hang of how to identify those patterns, these will become a lot easier. And I'll be perfectly honest, I don't think we will be asking anything quite at this level. I hesitate to say that this is a hard problem because it's considered to be an easy problem in the broader world of computer science, but it is probably a more difficult thing for someone who's been looking at recursion for 2 days. So yes, let us keep moving. Okay, it is already 7 o'clock, so I have maybe been talking for too long. The last question is on binary search trees, and binary search trees are just the same thing as binary trees. I was trying to find the picture. They're the same thing as our good old-fashioned binary tree, except now they have these 2 special conditions, that the value in every node is greater than any value stored in the left subtree, and it's less than any value stored in the right subtree. So they're a little bit more like organized version of the standard binary tree. So everything to the left would be less than, everything to the right would be greater than the current node. And we're just asking you to find a value in a given binary tree. So you're just searching through the binary tree. It's the same node setup that we had before, and it is the same code structure. I would say this question is slightly simpler than the previous question. It requires less lines of code anyway. So if you have time to practice on it on your own, I would suggest that. It might be helpful just to see if you can tackle this. This is also kind of a standard computer science problem, interview question on the easier side. So if you think about this question, maybe I'll give a hint. You know, what is an easy way to search an organized tree for a value? If you know what, if you know that all of the values to the left are less than and all of the values to the right are greater than, right? So if you have that information, how would you change the way that you search the tree? If you're looking for a specific value in a tree. So that is my words of wisdom for today. That's it. Thank you for stopping by. Always appreciate having a crowd. Keeps me going. Enjoy the rest of your week. Enjoy your quiz today. That's all.